Good morning, Just. My name's Peter Wilson. I'm the Technical Director of the INVC. I have been doing this for a very long time. I'm an engineer by training. And this morning you've heard from Chris at the HSE and from Sarah, ex-HSE and so on. And there have been words like frustrated is the word they've been using. The HSE have to be fairly politically correct and careful what they say. You know, I've been doing this a long time and I'm not frustrated. Well, I am frustrated, but I am utterly pissed off with the fact that not much has changed in 40 years. The technology's moved on, the ability's moved on, but people aren't using it. People are still going deaf unnecessarily. And it has a massive impact on people's lives, quite apart from the financial ones. And as an engineer in this area, I'm quite a bit slightly unusual in that I wrote the IOSH competency training course that we run. So we see a lot of reports and so on, and the standard is abysmal. In terms of noise control, it is terrible, and there's really no excuse anymore. It's just lack of knowledge. So what I'm going to be trying to do is to really, in the short period of time, to say I can't really go through everything, but what I can do is give you hope. That just to change the attitude of people to noise control. Noise control is regarded as an add-on at the end, not designed in. And the number of times I go to site to look at a piece of plant that's just been bought or just been installed, and I look at it and go, if only they designed it slightly differently, this would be easy. But it's very rare we get asked in to help design things. I can walk, I've been doing this for so long, in 40 years, I can now walk through most industrial sites and go, easy, easy, I need to look at that one in more detail. That one, I'll give you a you are doomed certificate, there's nothing you can do, you're going to have to use PPE. I can do that on a petrochem site, I can do that on a chemical site, I can do that in a construction or a demolition site. I cheat, I've seen in most things. But it's a lack of knowledge and the lack of application of that knowledge that I find really, really annoying. And I'd say I don't have to be politically correct, so I'm going to be very, very blunt. And please ask questions as we go along. So I'm going to be talking about a few things you probably don't know, and attitude and diagnosis, which is the key to doing things the right way, and unfortunately most people seem to do it the wrong way. So you end up guessing and spending a lot of money unnecessarily, or not doing anything. I'm going to be looking at the engineering technology, the art of the possible, what can be done outside the normal enclosures and barriers and science and all the rest of it, and some case studies which I'm going to sprinkle throughout. And we did offer free consultancy to anybody in advance of this thing, and no one's taken me up. So either you haven't got much in the way of problems, or you're too shy. So if you've got any problems, please, this is an opportunity to talk about it. Also, we're a founder member of the HCA, which is gradually going to be having loads of best practice about noise management and risk control and noise control on the site as well. But I thought I'd start off just an introduction about the costs of having a noisy plant. And the costs we've talked about, some of them have been talked about already. Noise-induced hearing loss and tinnitus. What a lot of people don't realise is that people with noise-induced hearing loss have a 9% increased risk of dementia. It's the single most modifiable risk reduction measure you can take. If I remember rightly also, noise-induced hearing loss also has more impact on your life expectancy than obesity. This is serious stuff. This isn't just, oh, I can't hear the television so well. PPE, the cost of which Sarah's already talked about, we usually say between £50 and £200 per head per annum, as a rough idea. Also the hassles in risk management, policing, audiometry and so on, massive costs there. Communication, working conditions, noisy environments aren't pleasant to work in, reduced productivity, higher staff turnover, all those sorts of things as well. And the ongoing risk assessment reports, most of which are a placebo and a waste of time, that tell you what you already know. And people just repeat and repeat and repeat. I've got a problem, I've got a problem, I've got a problem. I've spent £4,000 this year on a report telling me I've got a problem, which is exactly the same as the one I had 2 years ago. Doing something is the key thing. Also, PPE doesn't work. HSC research proved this, but people don't understand how bad it is. If you look at the actual risks and so on, The sort of reports that we see, again, HSE research says about 2/3 of all risk assessment reports aren't worth the paper they're written on. Their word for not worth the paper they're written on is inadequate, but it means the same thing. Advice on making PPE work in practice is very poor, and noise control advice is virtually missing. Unfortunately, the general standard, both from end users and consultants, the standard of knowledge about noise control is abysmal. And it's not based on diagnosis. Most reports we see, the little bit of noise control is a paragraph that's saying, it'd be a really neat idea if you could try one of these things off the HSE website or work out a way of reducing the noise. There's nothing specific. And hearing damage due to noise-induced hearing loss is estimated to cost the UK economy between £5 and £7 billion per annum. So something has to be done, and noise control is a major part of that. But I thought I'd start off with just really rubbing it in and making you very, very depressed about PPE. Now, we also do hand-on vibration, and it's been very noticeable that over the past 10 to 15 years, the levels of vibration designed in to hand tools and so on has dramatically improved. And the reason there's been an improvement is because there's no PPE for hand-on vibration. So if you're an end user and there's no PPE, this is a very serious risk. Big claims, big payouts, all the rest of it. So they go to the manufacturer, Mr. Manufacturer, part of my purchasing is going to be based on vibration. Now, why isn't the same thing done about noise? Oh, because there's PPE. Correct use of this bit of kit means you use PPE with it. And you're assuming the PPE works. This are the payouts from noise-induced hearing loss costs incurred by notification year. This is taken from the Institute and Faculty of Actuaries. And you can see in 2014, it's near enough £400 million per annum. The insurance industry is saying this is not sustainable. Okay? Obviously, what we're doing now has not worked. You can see that. And it's not new knowledge. 40% of PP users get no protection whatsoever, HSE research. Performance, most of the remaining 60% is inadequate, and 14% don't wear them. This graph here is going back to 1996, and it's showing that on the left we have, this is the performance of plugs as given by the manufacturer between about 15 and nearly 30 dB. In practice, between 2 and 10 dB if you're lucky. Earmuffs, we're talking about sort of 20 to 25 dB typically. In practice, you're talking about 10, maybe 15 dB. Our rule of thumb is, if you want to ensure that people aren't exposed above 80, their daily dose, the maximum level you're safe up to with PPE is around about 90. Between 90 and 95, it becomes increasingly difficult to guarantee risk reduction. Sufficient risk reduction above 95, you're fairly well doomed unless you've got very, very tight controls. And yet people, 95 dBA is the dose of an employee, issue hearing protection, assume protection 20 dB, no problem. There is a problem. You've just seen the figures. They don't work nearly as well as people think. And it's not new. Some other things you don't know, or a lot of people don't really take on board, is that every time you add 3 dB to the noise level, you're doubling the energy, therefore you are doubling the risk. So if you knock 3 dB off the noise level, you've halved the risk. Now, a key thing about this is that quite often people, no, there's no point doing noise control because it's 100 dBA, we can maybe get it down to 95, but you still have to wear hearing protection, so what's the point? Because you're assuming hearing protection works. So if you've got noise levels of 95 dBA and you can reduce it by 3, 4, 5 dB, you're now getting into the range where hearing protection will work. And every time you halve the noise level by knocking 3 dB off, you have halved the risk. So if your noise level is 95 and you get it down to 92, you have halved the risk. That's value. 6 dB off is 75% risk reduction, and 10 dB is 90% risk reduction. And the most common mistakes is lack of diagnosis, or none. People just guess. They go, okay, let's put an enclosure on it. Let's put a barrier on it. Let's issue PPE. Let's whatever. It's an engineering problem that should be addressed as an engineering issue, so you have to do the proper diagnosis. Lack of engineering knowledge is the next thing about techniques and materials available and so on. And then poor diagnosis. And then also more knowledge about materials, because a lot of new materials on the market, some of the old materials on the market. For example, as an engineer, I love this stuff. This is laminated steel. This is sound damped steel. Now, how many of you know about this? Hands up. A lot of people from the IOA and HSC have got their hands up, but 2/3, 3/4 of you don't even know about it. It's only been around for 45 years. You know, it's cheap, simple. I like it because it's cheap, simple, and robust. As an engineer, I can say, change this for this. You'll get 10 to 15 dBA off, cost you nothing. Works just as well, just as robust, hygienic. Why aren't you doing this? So you've got a few noise control techniques. One is engineering control, which is source control, which is the best way of doing it. Then you've got silencing at various times for aerodynamic noise sources such as fans and pneumatics. And you've got vibration damping, which is how this works, and a couple of other things as well. You've got vibration isolation, which is preventing the transmission of vibration into loudspeakers like Chris was talking about. You know, you have a vibrating source and you attach as much stuff to it as possible to create the biggest loudspeaker you can, so it's as noisy as possible. You can also put the old traditional enclosures around things, and you can modify area acoustics, but that becomes extremely expensive. But it's deciding what do you use, what's going to be the best way, what's the best approach. And there's only one thing you can do, which is accurate diagnosis. And it's a very simple process. But I thought what I'd do before I start in that is to say there's hope. This is a current project, so I can't give you any details or I have to kill you. This is a manufacturer of fans in America, dust control fans, and they asked us to look at the noise because they had lots of complaints because it's hearing damage levels as used. The first prototype now, based on our designs, is 4 dBA quieter, 10 dB off the tone, which is annoying, so it's down from 85 to 81 dBA. But that part of that redesign, 27% increase in flow, coupled with a 16% increase in head pressure, coupled with a 7% decrease in power output, in power required to drive the fan. And by the time we finish, it's going to be another 3 dB quieter than that. So fundamentally, even if it wasn't noisy, you'd still do these things because it improves the efficiency. So this is what I'm talking about, is that noise done properly. Noise done properly is self-financing in a lot of cases. Now this has cost them nothing because that fan is going to cost the same to build as their old one, it's just better designed. So I'm going to talk about attitude and diagnosis now, which is the key thing about just the way you approach noise, the way you think of it. Because if you think of it the way most people think about it, just add-on stuff, it gets in the way, you can't clean things, makes maintenance more difficult and so on. But if you look at it positively, saying we can actually improve your plant as part of the process. But this attitude is a real big problem. I've used this before. This is a grain dryer on a hill in Lincolnshire. And when they started up, everyone for miles around complained, jet engine on top of hill, you know. And so the manufacturer had heard about the technology we've developed to reduce noise from fans by changing the aerodynamics. It's a bit like Formula One. We design inserts that fit inside the fan casing which take away the noise at source without affecting the performance. So the manufacturer, we designed it, the manufacturer fitted it, everyone was happy, local authorities were happy, the environmental health officer was happy, but the farmer wouldn't pay because he said, where are the silencers? He's saying, I've got noisy fans, you need silencers. Is this some kind of con the manufacturer trying to pull? There's a switch around the back, there's noisy, quiet, more money, less money. So we had to design and fit resonator silencers unnecessarily. They did knock another 3 dB off, 3 or 4 dB off. They were placebo silencers fitted to get paid. This is about attitude. And the diagnostic process, which I'm going to very quickly run through, is the key to effective noise control. And you should only use the conventional palliatives if you can't engineer it out. Now, if you can go back to the design stage, it's so much easier when you've already got a piece of kit that's on site. People allow bits of kit to come on site which are noisy, despite the fact they might have a noise purchasing policy. Would you allow a piece of kit to come on site that gives off dangerous levels of fumes? No. Which is electrically unsafe? No. Why is noise different? Are you going to make 10% of your workforce suffer from dementia when they're older? few other things you might not know. Say aerodynamic noise control, which we use a lot for both occupational and environmental noise, is quite cunning. Materials and technology, and sound damp steel is one of them, the laminate and so on. And materials, this is another one I like. This is made by Ecofon, which is a completely cleanable, hygienic acoustic absorbent. Most acoustic absorbents, things like foam, rock wool, fiberglass, and all the rest of it. This stuff is got this rather clever film facing, which is extremely strong, completely waterproof. You can clean it with anything. You can use it in very high hygiene environments, like the food industry. Now, a lot of food industry noise levels are sort of mid to high 80s, low 90s, easily reducible to below 85, and this is one of the techniques. But people don't know about it, so they go, oh, no, I can't put absorbent in, or someone's recommending rock wool or whatever. So, metamaterials, which Dan from Sonobex we're talking about later this afternoon, very clever, I love that. They've developed this technique. You can have a see-through barrier with holes in it, and it stops the noise coming through by using cancellation technology built into it, so he'll talk about that. But let's give it another case. I mean, I may be very sad, but this is quiet sellotape, and I just think that's so cool. You know, I should get out more perhaps. Fundamentally, you know, you say, why is sellotape a problem? Well, if you've got a wrapping machine at the end of a line, putting things in boxes, like in Amazon or whatever, they're ripping tape off at high speed, wide tape. Oh, you can get over 100 dBA. And I've seen people put an enclosure around a machine because of that. Why not just buy quiet tape? Okay? Isn't that cool? And here's a demo we did for a client. Seriously? Make it out of this instead and look at the difference you get. Lack of knowledge. Okay, so the diagnostic process you need to go through is quite simple in principle, but virtually no one does it. So first of all, you have to restrain human nature. Human nature say, how do you make this quieter? People will start guessing. Oh, you could do this, you could do this, you could do this. You have to stand back and say, on this piece of plant, I make a list of all the noise generating mechanisms. And then I need to rank them in order of how much they contribute to the overall noise level. Once I've done that, I look at the dominant noise source, the loudest noise source, and I say, is there something I can do about this? If you can't, you have to fall back on enclosures and barriers and all the rest of it. If you can, you're on to a very cost-effective, very cheap noise control solution. So so listing and ranking, you do that. And the way you can, I'll talk a little about how you do that. Once you've got that ranking, and you're looking at the dominant noise source, if there's something you can do about that, then you're thinking about what are the operational productivity hygiene constraints on this. There's no point designing something you think is very, very clever. If the operator doesn't like it, he'll arrange to have it run over by a forklift truck before you leave the building. So you're not just looking at noise, you're looking at the engineering, you're looking at the maintenance, you're looking at hygiene, you're looking at cleaning and all the rest of it. And of course, cost. And if engineering control is not possible for the dominant noise source, then you're doomed. You just have to fall back on conventional enclosures and barriers and things, but you've proved it. And the problem is most people go straight to that without even thinking about the diagnosis. And in an awful lot of cases, it can become self-financing, because if you can cut the noise levels enough, you don't have to wear hearing protection or do audiometry and so on. And in other cases, you can improve productivity. Unless you followed that, your noise control is based on guesswork. And part of our Buy Quiet template purchasing policy documentation is a question for the supplier saying, you've got these noise control or a quiet version of your plant. Can I see how you arrived at that? Where's your diagnostic process? Can you talk me through it? If they can't, they've guessed. And it's very unlikely their noise control stuff is of any good at all. Another useful way of thinking about it is aerodynamic noise sources and mechanical noise sources. Aerodynamic noise sources generate noise directly in the air by disturbing the air. So that's pneumatics, it's fans, it's combustion, things of that ilk. Mechanical impacts are vibration energy fed into a structure that acts as a loudspeaker. And here's an example. Can you just about hear that at the back? Okay, if I put this on here, so why is it so much noisier?
Table amplifies sound.
It does in a way, yes. This is a vibration source, okay? It generates, but it's small and stiff, so it doesn't act like a good loudspeaker. So, but you feed that vibration to the tabletop, and this acts like a big loudspeaker. And this is such a common problem. Hydraulic power packs are exactly that. You have a motor pump unit, which is stiff and not very noisy. So what they do, the manufacturer goes, well, I need to show off the noise generated by my product, so I'm going to bolt this onto an enormous oil tank to make it as loud as possible. Now, one manufacturer said, this is loud. What we're going to do is put an enclosure over the top of the motor pump unit bolted on to the tank. An acoustic enclosure to reduce the noise. This actually increased the noise by 3 dB because you just bolted a bigger loudspeaker to your noise, your vibration source. But this is the thing. That manufacturer and an awful lot of people in principle, what they're doing is they're saying, we have a noise, the only solution is to put it all in the box. They don't think about why is it noisy, let's just disconnect it. And if you do that, 30 or 40 quid's worth of vibration isolation and some flexible pipes, you've got 10 to 20 dBA off the noise without interfering with temperature, because the box makes the temperature rocket, and it doesn't interfere with maintenance because you can see a leak which you can't see inside an enclosure. So here's an example here of what the power of why the dominant source ranking is so important. What we have is a machine. We've got a very simplified machine here. We've got a pump, we've got a fan, and we've got a motor. Okay? You run them all together, and you get the red one, which is the total level, is 95.5 dBA. And now, by some miracle, you can run each source completely separately. So what you're getting is from the pump, we're getting 93, from the fan, we're getting 90, and from the motor, we're getting 88. Now, the fan sounds noisy because it's got a drone to it, so subjectively it sounds the noisiest. So you guess, and you fit a good silencers to it, which reduces the noise from the fan by 15 dB. And then you add them all together again, and it's gone down from 95.5 to 94.5. You've got 1 dBA off because you haven't tackled the dominant noise source first. You have 2 noise sources of equal amplitude, and you completely eliminate one, you get 3 dB reduction in noise because you've halved the energy. So unless you tackle the dominant noise source first, you're doomed. You're not going to get a good result. But that's the key thing, is to work out what the dominant noise source is. How you rank them, you can listen, but be aware that to the untrained ear, you're going to be deflected by subjective impressions and not the overall noise level dBA, which is what you're interested in. So that's a clue, but also you can say, looking at my noise meter, the needle moving around, and it goes bang, bang, bang when it hits the end stop. So you go, that's the noise source contributing most is the end stop, perhaps. Or you can run each source separately. So we quite often will get a maintenance fitter to frig the interlocks, obviously safely, but normally you just press a button and everything starts up at once. But if you do the interlocks, you can then press that button, you've disconnected a motor by taking the drive belt off it or looking at one of the sensors or something. So you can try and run each noise source separately and measure the noise. How does it change? Or you can cover and uncover each source in turn. And we use barrier mat. And what you do is you cover up 3 or 4 noise sources, all of them, and then you measure the noise and you open each one in turn, and there's your ranking. Sometimes we also use more sophisticated techniques, which are narrowband frequency analysis. So if you've got tonal noise, it's a very, very powerful tool. And you can also do things like measuring with a microphone close in and calculating the sound radiated by certain parts of a machine, or you can do that with vibration as well, but those are slightly more sophisticated. But it's the basic concept of trying to work out the ranking of the noise sources that's the key thing here. Let's take an example of an electric drill. Unfortunately, I couldn't carry too much stuff here, so I haven't got a sample. So imagine, how many of you have done DIY work with a Black & Decker drill or something, drilling into concrete, or putting a shelf up in the bathroom in hammer action. How noisy is that drill? We have and horrific from here. Any advance on horrific?
About
100, 105, something of that order. So, are you desperately reaching for earmuffs when you're doing that, or earplugs? Some of you are, but others are going, what? Okay, well, you see, the thing is that drill is massively noisy, but you're not really aware of how bad it is because you're making the noise. And I can prove this to you. That one of the big problems with noise is this subjective component, is that you've finished putting a shelf up, it's beautiful, level, good stuff. Go downstairs, open the fridge, nice beer, well-earned beer after doing all that DIY, and your neighbour starts drilling into the wall on their side. It's 40 dBA in your lounge. Jesus Christ, that's so annoying. That's so 105, not bothered. 40 because you're not making the noise. And this is one of the big problems. You know, if your plant, your machine, you're the operator, you're the engineer who knows about it, you are not as disturbed by the noise as you should be. Now that drill, how are you going to reduce the noise from that drill? Just run it, let's simplify it. Running it in free space, it's about 85, 90 dBA. You want to reduce that noise. How are you going to do that? That's not reducing the noise, is it?
No.
The hierarchy of control is do-do-do-do. How are you going to reduce the noise from this drill?
I think it makes it noisy is sort of a hammer setting on set.
Well, yeah, but I've cheated. I've taken it out of the equation. I've said you're just running it light. Yeah.
Motor
So the
noise?
dominant noise source, which might be the motor or some kind of fan inside the group.
That's good. That's a good starting point. How are you going to determine what the dominant noise source is? Make a list. What are the possible noise sources?
Attachment,
Gears.
Gears,
fan.
fan.
The speed at which it's
Someone said motor. You've got gears, you've got fan, you've got motor, and you've got casing radiated vibration, which is from the motor and from the gears. Okay, so you can't walk up one end of the drill and measure it and go, oh, it's louder at this end than the other end, because it's only a little thing. So how are you going to separate those out? How are you going to rank them?
You could cut the inlet to the fan to suppress the action of the fan.
Yeah?
Frequency analysis.
Yeah? That's fundamentally what you do. That you can either take the fan off and run it, so you've got all the other sources but no fan. You only have to run it for 10 seconds to get the answer, so it's not going to overheat. Or you can tape up the intakes and the outlets, which gets rid of all the air paths, because the fan is an aerodynamic noise source. And if you do that, you find it drops by 6 dBA, which tells you that 3/4 of the noise is from the fan. So by doing that, you've ranked the fan as being the dominant noise source. And unless you can do something about the fan, you're doomed. So it's reduced the complicated problem to can I do something about the fan? So that's the sort of thing we're talking about. And here it is. Here's the narrowband frequency analysis of the noise from the drill. And here we have the tones. That's the rotation. That's the fan blade pass and fan blade pass times 2. They are the dominant noise sources from that piece of kit. That is the dominant noise source. I've got a couple of examples here. One is a power press. This is a very old video when I had hair, but it's still applicable. It's just showing this process in action.
Guessing which noise to silence and guessing wrong is one of the main reasons people find noise reduction at source so difficult. There are several major sources here. The most obvious are the tool impacting on the raw sheet, the noise caused by the air jet clearing the product, and the mechanics of the press itself. Which do you think is actually the loudest? On which should you concentrate your noise reduction budget? Intuition suggests the impact noise of the tool. Intuition is a major problem. It's not an effective or reliable measuring system. When you're faced by a complex system in real life, it is that much more crucial to do careful diagnostic testing. Isolate each source and measure how much noise it produces on its own. In this case, it's not possible to run the press without the air blast, but it is possible to run the air without the press. 101 dBA with the press working 100 with it off. Clearly, the main problem here is not the impact noise made by the tool or the noise of the press mechanics, but the aerodynamic noise made by the air jet, which is perhaps no surprise. It is very crude, just a flattened pipe. To reduce the noise output here, you simply fit a proprietary quiet nozzle. The cost? Not more than £15. 95 dBA, a significant reduction. This jet could also be fitted with a switch so that the air blows only when necessary, which is perhaps for 20% of the time. That would further reduce the noise dose of the operator and would also reduce compressed air consumption, a significant cost saving. Should the level still be too high, you simply go back round the loop. First, establish exactly what is the highest remaining sound source. Having reduced the noise produced by the air jet, the meter suggests that the impact noise of the tool is now the major contributor to the noise output of the machine. One way to test that is to shear grind the tool. After shear grinding, we found a further 4 dBA reduction, and once again achieved at almost no cost. Again, there are ancillary benefits. In this case, it reduces press loading and wear. The result of this simple work has been an average reduction in LEQ of about 9 dBA. That's not bad for a start. In fact, much what you'd expect if you tried to fit acoustic guards to the whole machine.
Any comments on that? That's just showing that in action. Using a power press, because this is one of the conventionally is one of the things you just stick an enclosure around it because there's nothing else you can do. I've got a couple more examples, but I will skip over those because we're very short of time. Someone mentioned frequency analysis. When I set up INVC 35 years ago, near enough, we bought a narrowband frequency analyzer and it cost about the same as a car. Now you can do it for free on your phone, and it's just as good. Maybe not be calibrated, but that's irrelevant in most cases. So as a diagnostic tool, if there's tonal noise from a noise source, you have got an absolute measurement that's quick and easy to diagnose that fact. This is an environmental one, but same principles apply. Someone complaining about hum from a plastics factory down the road. So which bits of plant is it? You can't tell someone to turn everything on, off in a factory and then turn everything on one by one. So go along and I measured close to the 2 cooling towers and a grinder to get the frequency characteristics of each of those. And then measured in the house, and we get a tone. And if we zoom in on that, you can see that this is next to the 2 cooling tower and the grinder, and this is one of the other cooling tower. That's the only one that matches the other. This is a 1 hertz different, so it's not that source. It's very, very precise. So we've reduced the problem for a complicated one. What on this site is causing the problem down to the 2 fans on this cooling tower are the cause of the problem. What we do about that. It's a very powerful technique, and I'll be showing another few examples. And I say you can do it on your phone for free. And you don't really need a calibrated one. All you're trying to do is because the frequency you get off your phone is exact. If you're using the phone microphone, it decays the low frequencies, but the relative amplitude of the tones is correct. So you don't need to do anything more. You can use a mobile phone is a very good, simple tool, and not used by very many people, which it should be. This is an example of the diagnostic process on a VAX vacuum cleaner. The manufacturer wanted to make it quieter for obvious reasons. They are noisy. But you've got a VAX vacuum cleaner, and my first question was, how much added cost we put on the vacuum cleaner to make it quiet? And they said, well, about 10p. You know, it's not willing to invest. This is a mass-produced product, so you know you're talking about fine margins. So he said, I don't want to spend any more money on this. I just want the design to be better. And so you're saying, okay, so let's look at a vacuum cleaner. Let's remove that so you can't cheat. Okay, vacuum cleaner. What are the noise sources? How are you going to reduce the noise from this machine? You know, you've got your sucky bit. Obviously, it's a technical term for doing all the cleaning and the rest of it, and you get noise from that. But what about the device itself? Where's the noise coming from? How are you going to reduce the noise from that? Sorry?
The motor again.
Motor,
Vacuum
fan, bearings,
Inlet,
inlet, outlet. Yeah, pretty well, most of the sources. There are two fans. There's a suction fan and there's a motor cooling fan. So there's two fans actually. Inlet noise, outlet, suction noise and outlet noise and vibration from the motor and so on. So how are you going to rank those? See, this is the hard bit.
See which bits you can run separately.
Yeah, running things separately was by far the easiest way, and you can do that because you've got complete control over it. So first thing we did is remove the motor cooling fan. The motor cooling fan was the dominant noise source. Bad design with bad airflow. But that left a really big hum, so we vibration isolated the motor from the casing, got rid of that. And then the air exhaust, where the air came out through a narrow slot, regenerated noise, so we smoothed that off in prototype form. A lot of blue tack was used in this process, so very, very, very technical. I really love that, going to site, and we've got all the good kit, you know, narrowband frequency analysis, accelerometers and all the rest of it, and you say, have you got any cardboard and some wide tape? You know, I love that sort of mechanical thing. Anyway, so we did all this and got very good result. But another problem that happened was that we did a pre-production prototype, a very early prototype, and got massive noise reduction. And then they did the next stage on before they go to production, and the noise level had jumped up again. And I said, what have you changed? Nothing. They'd only changed the motor and fan unit, but because it's the same duty, as far as they're concerned, it's identical. It just happened to be 5 dBA noisier. And this is a very common problem. People just don't think about noise as part of the specification of a device. So anyway, long story short, we cleared that up. Modified and unmodified, if you'd like to lift your feet up. That's 10 dB quieter and got rid of the tone, so it sounded much, much better. We deliberately didn't do anything about the suction noise because it makes it sound more powerful. If you make that bit quiet, people go, well, stop doing anything. You have to make the sucky bit noisy as possible. People go, oh, I can suck curtains off the wall at 10 paces. Another PowerPress one. This is, you've probably lain in bed wondering, how do they make the holes in the drum in my washing machine? Is that the sort of thing that keeps you awake at night? Well, this punches holes in sheet that's then rolled into the drums. And the whole workshop's 102 dBA at a meter. And the whole workshop was a noise hazard zone, a bit like what Sarah was talking about earlier. Lots of other people working in that area not doing noisy things. And they were going to spend a massive sum of money on enclosure, but they asked us to take a look at it. And so we did the ranking, the diagnostic ranking. So number one, the tooling, the impacts were the dominant noise source. So shear tooling on that took it down from 102 down to 97. The next dominant noise source is the air clutch, bad exhaust silencer. Fixed that down to 95. The third was the scrap extract fan. Fixed that down to 92. And the cyclone separator on that, fixed that down to 90. And then the outfeed, the final thing was the strip on the outfeed was acting like a big loudspeaker. So I designed a simple vibration damper that went onto that, which got it down to 87 dBA. So we've gone down from 102 to 87 dBA. All those modifications cost them around about £2,000 rather than £35,000 for an enclosure. And it doesn't affect access or maintenance, and only the operator has to wear hearing protection. The rest of the workshop doesn't. That's the power of accurate diagnosis. Another one, a vibratory grader, which was purchased subject to our purchasing policy. They use our purchasing policy. And it was picked up at the supplier. So this is noisy, this is 99 dBA, and our purchasing policies say it has to be at 80 to 85 maximum. So they got us in to look at it, and again, this is processing product that's sweets or tablets, go through the line, get vibrated. Let me just show you the video. And what we did to get the diagnosis was very, very simple. We just put a slug of product through, so you can see the noise. As the slug goes past each part of the machine, it tells you how noisy each part of the machine is, so you can focus your efforts on the highest noise level component. So, and you measure the noise as it goes through, and you can see from this graph here, you've got which parts of the machine, the noise levels, and sometime later, some damping, use of this stuff, and a few other geometric and other modifications. The retrofit cost was about £4,000 on a machine costing £250,000. If they designed it, and the thing about that is if they designed it in the first place, it would have cost them about £1,000, and they could have done away with the £25,000 of enclosure they had over the outfeed. So it would have saved them £24,000. They could have made £24,000 more profit. We were down to 85 dBA without the enclosure from 99. So, yeah.
What measures did you take?
A lot of damping and detuning things.
The sweets are hitting a panel that is noisy.
Yeah, if you hit a panel made of this stuff, it's 15 dBA quieter. And geometry was some of the other things to do, and also the way the vibration was fed into the thing. This was quite noisy without product, and that's just bad design. It should be a low frequency hum. So we redesigned the vibration isolation system and the way it was all mounted to get rid of all the inherent machine noise as well. But the thing about all these processes, there's no guesswork involved at all. You're doing things in exactly the right order to get the maximum effect for the minimum cost. Here's a slightly weird one. Okay, forklift truck, noisy at the operator, want to get the noise level down. How are you going to tackle that? Sadly, there's a clue in the photograph. Damn. How did you guess that? Yeah. Yeah, I mean, basically, you're inside and you go, okay, what are the noise sources? What are the noise sources that could affect the driver? Diesel engine, so you've got diesel engine noise. But diesel engine is just not diesel engine noise. It's caused by various parts. You've got the mechanical noise off the diesel engine. You've also got the fan, the cooling fan. You've also got a hydraulic pump, which is driven by the engine as well, which drives both the lifts and also the vehicle itself. So doing the diagnosis, the simple thing, we just took the cooling fan off and ran it. It's much, much quieter, 6 dBA quieter. So okay, what you do is you switch the agricultural cooling fan for a more sophisticated electrically controlled one, so it's not all on all the time, and it's much, much quieter. But in this case, this is another case where your ears are deceived, because this is 6 dBA quieter, but it sounds louder. So that's before. So that's 75% less risk, but much more annoying. So you're trading off, and the reason is because the fan generates broadband boring noise, which hides the highly tonal content, as you can see of the hydraulic motor, hydraulic pump. So it sounds, you swear blind it was louder, but it's 6 dBA quieter, which is 75% reduction in risk. And some more diagnosis. It's a cooling tower. They've been told by the manufacturer they need to get a new cooling tower head. It's at 31 grand. They sent us a video and a recording of it. So a narrowband frequency analysis of that, and a drawing of the gearbox. An hour later, it's the pinion. It's vibration from the pinion being fed into the structure. The simplest thing to do is to refurbish that gearbox, and if it's a continuous problem going on in the future, that's the problem. There's a problem with the gearbox design. The pinion wears far too quickly. Improve the quality of those two gears, and you get rid of the problem. But this narrowband frequency analysis is very, very precise. It's the tooth meshing frequency of the pinion in the gearbox.